Assalamu alaikum. In the last video we have studied an RLC circuit connected to an AC source. Here, to make this RLC circuit, a resistor, an inductor and a capacitor are connected side by side. Whenever components are connected side by side, we call such a combination as series combination. So we can say that the RLC circuit is nothing but a series RLC circuit which is connected to an AC source. When we do so, alternating current flows through these components. To the flow of current through them, a voltage is developed across these components. The voltage drop across R is found to be VR, and the voltage drop across the inductor of inductance L is found to be VL. The similar way, the voltage drop across the capacitor of capacitance C is found to be VC. Next, depending on the value of voltage drop across the L and C, one can decide whether the given RLC circuit is resistive, inductive or capacitive in nature. Alright? And there is one more method by which one can find out whether the given RLC circuit is resistive, capacitive or inductive in nature, by knowing the reactance offered by the inductor or capacitor. What is this reactance? In the last video I have explained you what is a reactance. Reactance is nothing but the opposition to the flow of current by a component other than resistor. If an inductor is nothing but a coil. When a coil or capacitor opposes the flow of current, then there the opposition is referred as reactance, whereas the opposition to the flow of current by a resistor is referred as resistance. So, in case of a resistor, we use the term resistance, whereas in case of inductor and capacitor, resistance is replaced with reactance. Remember this. And here, resistance is usually represented by letter R, whereas reactance is represented by letter X. There is one more thing called as impedance. About that also we have studied in last video. Impedance is represented by letter Z. The impedance is actually the collective resistance offered to the flow of current by a circuit. Suppose this RLC circuit opposes the flow of current. Then that opposition to the flow of current is referred as impedance, represented by letter Z. Remember this? We have obtained the expression for Z here. Now let's go ahead. To study this RLC circuit connected to an AC source, I take a phasor diagram. Now, in the phasor diagram, I have drawn a line OI, which represents current I. This is a phasor which represents current I in the circuit. I take this current phasor as a reference phasor. So with respect to this, the position of voltage across resistor, capacitor and inductor is mentioned here. Okay, how is it so? Let me tell you. Here, line OE represents a VR. Voltage across the resistor, of resistance R. Got it? Now from this, by comparing the phasor OI and the phasor OA, one can find out that current across resistance and voltage across resistance, that is a resistor R, lie in the same phase. See? The phase angle between them is 0. They are in the same phase. This is what it means. Whereas the line OB represents VC, voltage across capacitor C. Here, when it is compared with the current, you may find that the phase angle between voltage and the current is found to be 90 degrees. Okay, and one more thing here. I is along the positive axis, whereas the BC is placed in the downward direction, that is in the negative axis. This shows that voltage in the capacitor lags behind the current by pi by 2, by 90 degree. Okay, and next this line OC, it represents a voltage across the inductor. Now from this, if we compare VL with I, you'll find that here voltage across the inductor leads the current by pi by 2 or 90 degree. Here I have used the term pi by 2. Pi by 2. Here we know the value of pi in degrees. It is nothing but 180 degree. If you divide by 2, you get the value to be equal to 90 degree. Okay, so pi by 2 represents a 90 degree. This angle between the current and VC, or the angle between VL and I. You will see that. So pi by 2 means 90 degree. Now let me tell you one more time. Here VL leads the current by 90 degree, or this can be reversed, and we can say that I lags behind the VL by 90 degree. The similar way, VC lags behind I by 90 degree, or I leads VC by 90 degree. So these are the different way of relating current and voltage through these components. Okay. Now, one can easily say whether the given RLC circuit is resistive, inductive or capacitive depending on the value of VL and VC. How is it so? Suppose voltage across inductor is more than voltage across the capacitor. In such case, what will happen? We will draw a line, a phasor, whose magnitude is more than the phasor which represents the VC. So this is what we have done. Now see, OB represents VC, whose length is smaller than phasor OC, which represents VL. Now this shows that if you want to find the difference of these two, then by using head to tail method of vectors, now in vector addition and subtraction we use the head to tail method when two vectors are acting in the same line. Here we have two vectors, OB and OC. I told you when we use a vector to represent current and voltage, then we call it as phasor. Here we have two phasors, OB and OC. To find the difference between these two, to subtract them, what I will do, I will draw a vector whose length is equal to OB, and I will draw it in the reverse direction along the OC. This is what I have done. By doing so, whatever things that I get here, the remaining length will provide me the resultant vector. a resultant phasor. That's the VL minus VC. This is how we get it. Okay. Now, this shows that when VL is greater than VC, the resultant will have positive value, and it will show that the RLC circuit is nothing but inductive in nature. Okay. If VC is greater than VL, then we will get the resultant of these two will be equal to will be in a negative form. We'll get a negative value, and that will indicate that the circuit is nothing but capacitive in nature. Okay, this I am going to show you. Now we'll discuss few special cases. First, I'll take case 1, in which now I told you one can easily find out whether the given RLC circuit is resistive, inductive, or capacitive, depending on the value of voltage across them. Now, depending on the value of VL and VC. Similarly, one can also decide whether the given circuit is resistive, inductive, or capacitive, depending on the reactance offered by inductor or capacitor. How is that? Now I'm going to explain this to you by taking the reactance offered by inductor and the capacitor to the flow of current through them. Okay. First, I say that XL, inductive reactance, is found to be greater than capacitive reactance. Okay, this I am going to use here in this equation. We have tan of phi is found to be equal to VL minus VC upon VR. Okay, VL minus VC upon VR. Now here VR is present in the denominator, so the value of phi, phase angle, depends on the terms present in numerator. In the numerator we have VL and VC. That's why I told you the phase angle, or if you want to know what type of the circuit is, that can be easily obtained or found if you know the value of VL and VC. Okay, and here there is one more equation to represent tan of phi is nothing but XL minus XC upon R. Now when XL is greater than XC, it means the value of XL minus XC, the value of XL minus XC definitely is going to be positive. We will have a positive value. When it is a positive, then phi value that we obtain will also have a positive value. So we get a positive value for phi. If it is so, then the given RLC circuit will be inductive in nature. So the circuit will be inductive. Be inductive in nature. Okay, and the next thing here, when the given circuit is inductive, then we know very well current, and you can say voltage VL leads the current by angle phi, because it is a positive. Okay. So how do we represent current and voltage? There, current is represented as, right. First, I will represent the value of V. This is what a Vm sin omega t. Then I value is found to be equal to Im sin of omega t minus phi. Okay, this clearly shows that voltage leads the current by angle phi. Clear? Now I'll go ahead. I'll go to the next case 2. The second case, I take XL lesser than XC. If it is so, then XL minus XC, the value for this one will be obtained. XL minus XC will be a negative value. So 5 is nothing but negative. Yeah. If it is so, then the circuit, RLC circuit, will be capacitive in nature. The circuit will be capacitive in this case. Then VL, sorry, not VL, VC. VC lags behind I by angle phi. Okay, this is what it means. And notice so the value of voltage and current here, so V will be equal to Vm sin omega t, and I here will be equal to Im sin of omega t plus phi. This clearly shows that current leads voltage by angle phi, or voltage lags behind current by an angle phi. This is what it means. Okay. Third, suppose the reactance offered by the inductor XL is found to be equal to the reactance offered to the flow of current by the capacitor XC. In such case, the ratio of these two, the difference between XL and XC is found to be 0. In such case, I and V will be in phase. Means V equals to Vm sin omega t, and I will be equal to Im sin omega t. This clearly shows that the difference in the angle between these two is 0. It means in RLC circuit, voltage and current will be in phase. That means the circuit will behave as a resistive circuit. Okay. So the circuit will be a resistive in nature. Okay, will be a resistive in nature. Clear? Because the difference is 0 here. Alright. So from this one can easily find out whether the given RLC circuit is resistive, inductive, or capacitive in nature. I hope the video is useful. If you have any kind of doubt related to the topic, kindly put a question in the comment section. Thanks for watching.